Hello, everyone. Thank you for attending today's webinar, 5G Capacity Planning, Sizing in a Cloud-Native Environment, part of the 5G Core webinar series presented by Hewlett-Packard Enterprise and Intel. I'm Nancy Lickley, the Communications and Media Solutions Marketing Manager at HPE, and I'd like to share just a few technical notes before we begin. If you'd like to download the slide deck, please check the Resources List tab on the left side of your screen. This webcast is being streamed from your computer, so there's no dial-in number. For the best audio quality, please make sure that your volume is turned up. This webinar is being recorded and will be available on demand within 24 hours after the event. Time permitting, we will follow the presentations with a Q&A session. So please submit your questions using the Questions and Answers tab that's on the left side of your screen. Okay, now let's begin. Sue Rudd, please go ahead.
Thank you very much indeed, Nancy. I'm Sue Rudd, Director of Network and Service Platforms at Strategy Analytics. And our speakers today are Rob Heldenbrand, Senior Solutions Architect, HPE Communications and Media Solutions, and Declan O'Boyle from Intel's vRAN, who is Intel's vRAN Solutions Architect in the Network and Custom Logic Group that was formerly Intel's Network Platforms Group. I'm going to begin with an introduction, and if you would like to see more on the speakers, you can click on their bios on the bottom left of your screen. I'm going to begin with an introduction on the capacity planning as it is today and the areas where we think there is evolution that needs to take place. Rob will follow with some specific aspects of 5G capacity planning and some of the new challenges of cloud-native capacity planning. And Declan's going to talk specifically about some of the RAN implications in a very dynamic environment for 5G. So let me start with an introduction to how we do capacity planning today, and many of you will be familiar with the concept of a busy hour. And I'm not going to go through this in detail, but what we have here is an example from an Intel white paper with the sources at the bottom from SK Telecom, looking at different arrival rates for different user plane data, and you have 5 user planes shown in the chart at the bottom right. And you can see that they all peak at around the same time at between 1800 and 20 hours in the evening. So this is very typical that traffic on a network will have a particular busy hour peak during the day, and it may be longer than an hour. But typically in the past, engineers have looked at these and engineered enough headroom during the day to allow for sufficient capacity at the peak period. And often they've allowed a lot of headroom at the peak period to allow for redundancy and failover, sometimes between 30 and 50% capacity. So very often in traditional networking, we've never gone above 70% capacity utilization has been sort of the rule of thumb. But one of the challenges is in the new networks that we would like to get better capacity utilization and reduce the CapEx requirements for these networks, since there's a lot of wasted capacity. And when we look at it by application, as shown on the next slide, we have variations during the day for different applications. And historically, these have had separate peaks for voice, for data, for different kinds of gaming, which has now become that big evening peak. And we've seen a lot of commuter peaks in the past on mobile traffic, now moving to the evening video peak for mobile downloads for the millennials typically. But if we could only allocate resources that share the traffic across applications, these peaks could be significantly smoothed. And as we move into virtualization and cloud native, by handling the queues that develop for each of these applications, we can actually allocate the resources, and each application can be shared across all of the resources in the network, or at least subgroups that apply to that performance class. So that we hope to get from our traditional low percentage utilization maybe all the way up to 85%. And that would really dramatically impact the CapEx savings of the operators. 5G is going to present some really big problems, however, to go beyond where we have been traditionally. We're going to see peak data rates that are 10 times what we saw in 4G, and user data rates that are also 10 times, maybe even an average rate looking at 100 times that of 4G, which is what we're seeing in some of the trials. And then transactions and signaling rates are going to increase dramatically by 3 to 10 times. Those we saw in the traditional signaling over diameter and SS7 over the new HTTP2 signaling plane. And finally, the mix of traffic is likely to change. Those applications that really need 5G, such as interactive gaming with low latency, are going to be the early ones that move on to 5G. And user-generated video within the RAN is going to become a big issue, and we're going to see some very bursty video capabilities as users upload their video and share with their friends. So some very different traffic patterns than we've seen historically. So there's some new approaches that are needed. We need new technologies to handle these, and particularly starting with the new ways we need to handle cloud-native virtual resources and get to those higher load factors, to introduce increased redundancy because the bare metal solutions may only have 3 nines, not 5 nines, but by load distribution we can actually get higher redundancy across the resources that are available. And we may need to have some modifications to the traditional queuing approaches that we have used, and HPE is going to be talking about some of those. And we have new rules that are going to be needed to be developed by the operators that go beyond what cloud data centers have needed. Kubernetes at the container level has been sufficient for much of the management of the virtual cloud services that we need in a data center. But within the telecoms network, we need to manage very often at the microservices level and distribute microservices across containers or instantiate new containers, but depending on the microservices load. So another level of complexity is added by the network. And finally, the scaling requirements of the network are going to be significantly larger than those of the cloud data center. So there's some really tough problems here. So at this point, I'd like to hand it over to Rob Hildenbrand, who's going to discuss some of the solutions. Rob.
Thank you, Sue. My name is Rob Hildenbrand. I'm from Hewlett-Packard Enterprise, and I'll be discussing some of the differentiating factors for capacity modeling of legacy network functions and entities as compared to 5G's containerized service-based architecture. Then I'll be talking about some of the capacity modeling building blocks and deployment best practices to consider in your 5G core network. Then I'll explain how operators can use a multi-server, multi-phase queuing model to model the number of threads required to handle the number of incoming transactions and determine an estimated response time of the 5G core network that consists of these multiple containerized microservices. I will go into some of the basic queuing terms and formulas and explain how a nested queuing formula can be used, and then show some examples of how nested queuing formulas can be used to model the capacity and response time for the UDM authentication call flow. And then I'll wrap it up and show how it kind of relates to your operator's business. So in the legacy networks, network entities were typically deployed on dedicated hardware provided by vendors, and the performance characteristics were generally of these dedicated hardware, and the solutions were protected by the vendors as intellectual property. And the scalability of this was more at the solution level because of the stateful nature of the solution. So it has less messaging and fewer moving parts and fewer fault zones. But the stateless containerized 5G network functions, because it's deployed on a service-based architecture by the operator system integrator, there's going to be multiple moving parts, and also the hardware will typically be a cloud deployment, whether it's a private cloud or a public cloud. But most of these stateless multiple microservices, they're going to be architected to provide a specialized or common function. And with this, there's going to be more messaging on the control plane, more moving parts, and more fault zones. Thus, but the benefits, though, are the scalability that you get at the containerized functional level, and vendors are going to have to expose more of their performance characteristics of each individual function. And to model this, it's going to require a multi-server, multi-phase queuing model. The most influential performance characteristic in your 5G core network is basically going to be able to optimize your core plane network. There can be anywhere from 10 to 20 message hops between the 5G network functions and microservices, so any minimization of network transport latency benefits the entire solution. For instance, if an average network transport latency is 0.5 milliseconds and it takes 16 message hops, then you have 8 milliseconds of overall response time. That's just pure transport latency. In the same scenario, but with a network transport latency of 3 milliseconds, that basically adds 48 milliseconds to the response time just for latency. Therefore, operators and system integrators should do everything they can to ensure to minimize the network transport latency. And one of the best practices they can do is to consider co-locating these 5G microservices and functions in the same data center. Operators and system integrators will also need to understand how many message hops to different containerized functions and microservices it takes to complete the transaction. They will need to know every containerized microservice that's deployed in their network. And once they understand the flow of the transaction through these microservice functions, they'll need to know the certain performance characteristics and variables in order to model the number of instantiations required for each type of containerized microservice and model the estimated response time. Prior to deployment, though, some of these characteristics may not be available, and the operator will need to still model these, but use an assumption for the value. After deployment, then the actual measurements can be taken. You can compare it against your assumptions made in the pre-deployment phase. Parameters that are key for modeling will include the values for your facility characteristics, such as network transport latency and bandwidth, CPU speed, the arrival pattern of new transactions received into the queue per second, and the service time in milliseconds it takes to process a single transaction to completeness. Some service times will vary as they need to be based on the message type received. So this picture here represents how the response time, or total wait time W, is calculated for a single phase queuing model, which includes the mean service time plus the wait time in the queue plus the round trip network transport latency. Basic queuing formulas from a single server, single phase queuing model provides an introduction to project the total number of transactions in the system using formulas such as little log. These formulas can be used to model the projected total number of transactions in the system by taking the mean arrival rate times the total wait time. An expected time in service can be modeled by adding the wait and queue time to the expected service time, which is the reciprocal of the mean service time. These basic queuing terms used in these formulas are typically represented by Greek letters. So the Greek letter lambda represents the mean arrival rate of new transactions over a given period of time. The Greek letter mu represents the mean service rate for a single transaction. L represents the expected number of transactions in the solution. And W represents the wait time for a single transactions, which means the service time plus the queue time plus the network transport latency. The Greek letter omega, on the other hand, just represents the waiting time in the container, which basically means the queue time plus the service time for each individual transaction from the time it enters the container to the time it leaves the container. And WQ, of course, omega Q, represents the waiting time just in the queue. However, in the 5G service-based architecture, we need to use a multi-server, multi-phase queuing theory model, especially if the 5G network consists of multiple stateless, functional, or common microservices. A multi-server, multi-phase queuing theory model is useful for modeling a solution that has several identical servers or threads pulling transactions off the queue to be processed but yet it still requires a single transaction to traverse across a series of nested activities or individual processing points, with each having their own queues before processing is complete and a response sent to the VIA-most outer processing point. This picture shows three phases, one outer phase on the left and two inner phases on the right. The total wait time for the inner phases can be modeled using the basic formulas, which include the service time, the wait time, and the network transport latency. The total wait time of a single transaction can be modeled by following the path of a single transaction. So first, the transaction has transport latency to the outermost container to its queue, where it stays until it is pulled from the queue to be serviced. Then the outermost container has some service timing, but passes the processing to the inner phase, which also has the network transport latency, wait time in its queue, service time, and network transport latency for the response. Again, the outermost container has some additional servicing time, but then passes the processing to a second interface, which also has its own network transport latency, wait time in the queue, service time, and again, network transport latency in the response. Finally, the outermost container has some additional servicing time for this transaction before sending the response, which incurs one last network transport latency. The service time for the outermost container, though, must include the wait times for each nested phase or processing hop. The wait times for the innermost phases can be modeled if prior to deployment, if necessary. But an important factor to notice here is the number of network hops it took to process this example, which validates the need to ensure an optimized network for the control plane. Before I take you through some of these nested queuing formulas, I have some additional terms to introduce. C basically represents the number of active threads, and in this example, I'm using a 4-core container with 16 threads per core for a total of 64 threads. The Greek letter rho is the probability or utilization of the queue being empty, where the container is the utilization, where it's the expected inner arrival rate divided by the product of the number of threads times the expected service rate. And you want your probability to be less than 0, because when the utilization or probability is less than 1, then the solution is considered to be in a steady state, which means you will not overrun your queues. And then one last Greek letter is the sigma, which is the service variance, and that service variance is calculated by taking the difference of a minimum service time from the maximum service time and then divide it by 12. So let's walk through the steps to model the response time W and the number of transactions in the system. So first you gather your values for your arrival rate, service time, and number of simultaneous threads. The mean service time is 11, and the variance is calculated as 0.3333. The arrival rate for this example is 1.1076 transactions per millisecond, and we're basing this off a call model of an operator subscriber base. As I said earlier, the number of simulated threads is 64. So to calculate your probability or utilization, you would divide the arrival rate by the expected service mean time times the number of threads. Again, that probability should, as you can see here in this example, it's less than 1 and greater than 0. So this is in a steady state, which means we won't run over the queue. But in the event your probability is greater than 1, then you need to increase the number of threads in order to get your probability below the value of 1. The next step is to calculate the estimated number of transactions in the queue using the mean arrival rate, variance, and probability. And you take the square of the arrival rate times the rate of the variance and add the square of the probability, then divide by 2 times the value of 1 minus the probability. The next thing we need to calculate is the wait time in the queue using the estimated number in the queue by the arrival rate. And you take that number of transactions in the queue divided by the arrival rate to get that value. And then finally we get to the response time on how to estimate the wait time in the system. You take the wait time in queue plus the expected service rate, which is the reciprocal of the mean service rate. This value does not include the network transport latency, so we need to add the network transport latency of the inbound hop and the outbound hop of the outermost container. And in this model, we're assuming a 0.5 millisecond network transport hop in each direction. So our total wait time for this network function is 12.18 milliseconds. Then we calculate the number of transactions that will be in the system during any given millisecond, and you take the mean service time times the wait time in the system to get that value. So this is the model of for a end-to-end 5G mutual authentication. As you can see, there's 8 round-trip message hops that occur between the nested activities of each 3GPP defined 5G network function in order to authenticate a UE device. However, each network function is composed of several containerized microservices to provide stateless, scalable 5G network functions. The number of different microservices with each network functions are left to the vendor implementation. But by using the nested outer queuing formulas, operators can model the wait time and response time of each 5G network function via the outermost nested container of each 5G network function. There are 5, and in this example, you can see that there are 5 different wait times that can be modeled. Now, on the following slides, I'll model the wait time for the UDM's UE authentication service. So this is the interior call flow of a UDM network function, specifically for the UDM UE auth containerized microservice. We are assuming a network transport latency of 5 milliseconds for each hop. As you study the UDM interior call flow for the UE service, you will see that the outermost phase is the UDM UE auth containerized microservices of the UDM. And then the UDR network function and crypto commons microservice are interfaces to the UDM UE auth microservice. The interfaces can be modeled for estimated wait times, or you can use actual measured response times in steps 2, 3, and 4. And then the total wait time for the UDM UE authentication service is 12.2 milliseconds, which is the 11.2 milliseconds value we modeled from the previous slide, plus 5 milliseconds for the inbound network transport latency, and another 5 milliseconds for the outbound network transport latency. So I've talked about minimizing network latency on the 5G control plane and doing best practices like co-locating the microservice and network functions in the same location. Talked about how the modeling of the expected utilization to ensure a steady state deployment, modeling the response time, number of transactions, and number of active processing threads in each system for each containerized microservices, and how to use the nested outer queuing theory formulas to model a multi-server, multi-phase architecture of a 5G core network. But some of the benefits to these operators are basically that you'll get better utilization of your hardware resources, and also the minimizing the possibility of overload conditions and fault zone failures. You also are able to model a projected response time of each 5G network function, even in a multi-vendor deployment, and use these values to build an end-to-end response time budget for a given scenario prior to your development. And now I would like to turn over the presentation to Declan O'Boyle.
Thank you, Rob. So my name is Declan O'Boyle, and I'm a solutions architect in the network and custom logic group within Intel. And today I want to discuss the radio access network, the transformation that's taking place there, and what it means in terms of dimensioning and provisioning hardware, and how a generic processing platform or a cloud platform implementation can address those challenges. So the WAN is evolving, and this WAN transformation is much more than just a 4G to 5G transition. In this scenario, we see many of the core functions and new functions moving towards the edge of the network and residing now at the edge of the network. And things like new low latency use cases and 5G URLLC type implementations is creating that demand to put even some core functions down at the edge of the network. And at the same time, you will continue, the base station functionality will remain there. Now, coupled with that, there's also the motivation to centralize the WAN where that makes sense. So, the new WAN will have a mix of centralized and distributed WAN at various locations in the network. And coupled with that, then we talk about traffic growth, and Sue mentioned, the predictions around traffic growth. So, along with the traditional, enhanced mobile broadband that 5G will bring, the whole advent of network slicing also creates a new demand and a new way of, architect dimensioning the solutions that will exist at the WAN and the radio access and network. So essentially, there's lots of change occurring in the radio access space. So quickly to just touch on, when we talk about distributed WAN and centralized WAN, the top diagram here, essentially represents a, traditional WAN implementation. And this is now also, being virtualized and cloudified, so to speak. And one of the concepts here, and motivations for even virtualizing the WAN right out at the base of a cell tower, like in a rural type implementation, for example, the network demands, wouldn't justify that each operator place their own hardware solution at that site. And it's a much more efficient implementation if the vendors can share the solution, share a fixed hardware platform solution for that type of a rural application. And clearly there, a cloud-based implementation and a virtualized WAN implementation enables that to happen. And then when we think, to centralize, the industry is converging on these splits now in the sense of the radio and the base station processing. And thanks to initiatives like the O-RAN Alliance, there's kind of a convergence now around, segmenting the processing in these ways. And if I start here, if you look at the radio unit or the RF part, so that's the physical part, and that will always exist at the radio site. And indeed, as we look forward to next generation radios, that radio unit implementation or functionality is being integrated with the radios to have what we call, O-RAN compliant or X-RAN compliant radios. And then in terms of the distributed unit here, this is essentially the real-time processing that was typically, implemented in fixed function processing, very real-time focused DSP-like functionality. And then on the left-hand side here, we have what's loosely termed as kind of the centralized unit, or the non-real-time aspects of the processing. And that is more packet-based, and more like a core function. And typically, in the first evolution here, if we look at the middle diagram on the right-hand side, this was the part of the WAN that was first centralized because it was the simplest to do, and it had the less demands even on the interface between the CU and the DU. You had no real-time processing. You had you had more time in terms of latency across that interface. But as you look to, centralize that real-time processing and move the DU function to a centralized location, You now have to meet those real-time challenges, and you have to you have to have that transport infrastructure in place. Now, coupled with that, the motivation to do this is not only just a capex and maybe an opex motivation to centralize your DU. There can be things like real estate at the cell site. As we look forward now, and with 5G and all of the services and capacity that that will bring, some of these existing cell site locations are quite constrained physically in terms of physical space and the amount of racks. So there may be a great motivation, to move some of that processing. It simply cannot all fit at the base of the tower, and to centralize that processing in a centralized site. And that's the reality we see that's occurring today. So all of this, all of the net here is that all of these deployment models on the right-hand side will exist and coexist. It's not a case, of one implementation will fit all solutions. So as we move forward, then it's, this is where a Cloud WAN platform provides that flexibility and agility. So now, here when we talk about compute for the WAN, how do we dimension that compute, and what kind of parameters and metrics do we use? And I guess, a metric we've used here as we have developed our, software-based WAN implementations is around this, cores per cell. Effectively, the number of CPU cores it takes to process a given sector carrier. And, and that's specified then for a given sector carrier for a given flavor of CPU, how many cores that would take. And based on that number, then you can scale it and dimension kind of the type and size of a platform you would need to service the number of cells required. But, so how do we come to this number, and how do we determine this number? And I guess within Intel and within our group over the last number of years, we've developed this FlexWAN software reference implementation that is a blueprint on how to, implement the WAN in software in a flexible and scalable manner, and in a manner that works well in a cloud environment that can be scaled. And this FlexWAN reference implementation can then be used. You run your defined sector carrier configurations, you can program them into it, run them, analyze the results in terms of the CPU cycle counts, and do that even at a very granular level, at a module level within the software stack. And based on that, then you'll ultimately come up with effectively this kind of metric of the number of CPU cores per sector carrier required. So that gives a sense of how you can compute for a given a given workload or a given cell configuration, the capacity needed in terms of compute to deliver that. And then, when we have that number, and you think in terms of an operator that's deploying, provisioning the hardware at one of these locations. So, as Sue mentioned earlier, there's a level of overhead, always required and always baked in. And in a fixed function deployment, it's very important to kind of limit that over provisioned hardware. And if you think in the sense of, these fixed functions, that's dedicated 3G, a dedicated 3G blade or box, and a 4G blade, and now a 5G blade coming on stream here. And you dimension those, and then you try and predict the headroom required associated with those, and you add in that additional headroom there for each of them. So this headroom then, or this over-provisioning, can become quite significant, and in terms of, the real estate at some of these sites where it's very valuable, you have all this over-provisioned hardware. So there's a lot of focus to try and get that number right and get that very accurate, and not waste those resources, because they're essentially not generating revenue at that point in time. Now in a vRAN type deployment shown kind of here at the bottom, it's a very different concept. What you have here is a pool of compute essentially, that's used that hosts all of the workloads, be it 3G, 4G, 5G, new edge services, maybe core functions that need to reside there. So there's this pool of compute, and into that, of course, there'll be some headroom baked in. But this headroom, this over-provisioned headroom is a very versatile asset at the network location. And I'll go and show in a subsequent slide, some of the value and some of the areas how we can, utilize that headroom effectively. So just before we jump to that, I want to just, emphasize when we talk here about a cloud platform, we're not talking about a single box or a single fixed solution, or enclosure. What we're really talking about here is a common hardware architecture, that is used across all of the specific hardware implementations, such that the software that's delivered and the virtual network functions, etc., that can land on these locations is all landing on the same architecture and will run efficiently and effectively in any of these implementations. And on the right hand side here, I've shown like the typical form factors that you see through the network, from at the top where you're kind of a core network type box, your standard dual rack mount server type implementations like the ProLiant, the DL360 from HP, data center environment, data center solution. And then, with the advent of these new telco edge network locations where we see some of the base station centralization occurring, these new boxes now, such as the Edgeline 8000, like from HP, a sled-based or cartridge-based box that can scale in terms of the number of cartridges deployed, is the solutions that's gaining traction in these locations. And then further out towards the bottom of the cell tower, maybe those solutions then are like maybe single socket-based type solutions. And finally, at the bottom here, we're looking at small cell type implementation to pole mount implementations that would be custom designs essentially. But the key point here is they all come, the fundamentals of them all is this consistent hardware architecture, and by extension, the software implementation that runs and executes on those. So finally today, I just want to talk about getting back to the over-provisioning, of the network, and if you over-provision some of those cores. And what we have, learned here, what we can talk about here is the idea to leverage the investment in the network. And clearly, if you over-provision cores here in the network, one of the things, that can be used for is kind of this edge services innovation. This idea of, we've all heard a lot about edge services, and it's still everybody's, and particularly operators, are trying to understand, hey, how can I maximize the value of my network and get more out of it and get a better return on revenue. And this enables what I refer to as edge services innovation, the ability to innovate, at the edge of the network. And by having this type of an implementation here and a pool of cores and some overhead provisioned, that has reduced the barrier to entry to enable you, consider to trial new services, for example. And if you compare that against a scenario where, you have to bring in a compute box itself for that, that kind of innovation, then there's a lot of barriers to entry to do that. You need to get real estate in the site location. You need to get power. You just need to get it's a lot more difficult to do compared to a scenario where it's all there, the compute is available, it's already managed, it's already orchestrated. So it's a much lower barrier to entry to get involved, to get up and get running and trialing these new edge services from an operator perspective. So let me conclude here by saying that the planning and provisioning of the hardware at a given network location is not as maybe daunting as one would initially think, because the cloud platforms provide the versatility and agility to run the workloads that will generate the revenue. So thank you for your time today, and with that I'll hand it over to Sue for Q&A.
Thank you very much indeed, Declan. That was great. And as we move to Q&A, please note that it's still time to submit your questions at the Q&A button on the left. And we have a lot of great questions already, so we'll try to get to as many as possible. If you'd like to download the slide deck, please click on the resources button, also at the left side of your screen. So let's go to our first question. So Declan, that's very exciting stuff about services at the edge. I think is one of the hot areas that service providers are very interested in. Could you maybe say a little bit more about some of the things Intel's doing to help with actually calculating how much storage and compute you need for those with the new openness initiative and how that aligns with the FlexRAN and other Intel initiatives? Are they the same thing? Are they different things?
Sure. Yeah. So no, that's a good question. I mean, the openness is, they're similar things, and I guess in a way, our FlexRAN is a subset of the openness initiative. The openness itself is a software toolkit, that helps and facilitates and enables the orchestration and management of the network. It's orchestrating the containers and how the whole network is managed, and bringing up and bringing down those compute resources. The FlexRAN, on the other hand, is a subset of that. It's one of these edge services, or one segment of these edge services. It's essentially, be it a 4G or 5G base station function that would reside, as a service. And the FlexRAN itself is a blueprint on just how to implement that in a cloud environment and under the whole openness infrastructure that is being promoted by Intel. And indeed, it's like openness. FlexRAN is an open source software implementation. The licensing is a little bit different, but it is available to the RAN software vendors to enable them to, as a blueprint on how to develop an efficient and effective software-based RAN.
Oh, that's great. Very helpful. So let me ask both of you, have you seen any examples of the big changes in performance characteristics, and what's so different about 5G? Maybe Rob, if you can comment first.
Sure. So for the control plane, where we're seeing the biggest example of change is basically in the increase in number of messaging it takes just to register and authenticate a 5G UD device on 5G network, as compared to like what a 4G registration and authentication would take. And that was our first indicator in regards to the increase in response times and additional hardware and networking resources it's going to take just to support the 5G model of stateless network functions. And we just kind of look at that. That's the cost of doing business on 5G, so that you can get the benefits that are promised by the 3G, 5G architecture.
So Declan, what are you seeing from Intel's perspective?
Yeah, so I guess maybe with a RAN kind of a view of this, I see that one of the the key areas when we talk about 5G is it's around the low latency, and I think this new use case such as the ultra reliable low latency, the name says it all. It's a big challenge, right? Like it's a big jump in performance in having an ultra reliable low latency implementation, and that really is driving these functions out to the very edge of the network. And as we look to smart factories, and there's a lot of excitement around this and a lot of potential in this, and it would bring real value to factories, etc. if this to implement this. So I see this as the real big one from the RAN perspective. And when this gets delivered, it will really change the RAN.
Sure, and customers can't be waiting for new capacity to be instantiated if they want a low latency service.
Exactly. They need it now.
So maybe you can comment about how much more complicated this gets. So you mentioned the factory, but even within the network, we're seeing more and more of multi-vendor environments with VNFs from different vendors running on the same platform, potentially, ultimately, even if not today. How is that going to work out when we need to allocate hardware resources across vendors?
Yeah. So as we look at this again, I think because if we look back to that generic compute pool, in the first instance, you'll get a broad sense of the requirement needed by the various vendors running, we'll say, on a common platform. But then, you'll over provision and you'll have a compute pool there to allow for to provide flexibility and allow growth between the vendors, because you don't know maybe how the market segment will change and which vendor will demand more solutions. So in that sense, the agility and the flexibility of being able to dynamically provision hardware and allocate it at that container-based type level to the various vendors, makes all this possible. And then coupled with that, these new hardware platforms like the Edgeline 8000, that's a sled-based solution. You can plug in number of CPU-based sleds. So if you see your capacity demands increasing greatly, it's not that forklift type activity that was in the past to just add in more sleds here. It's a much more less of a task to do that and easier to implement, because it's all already orchestrated and managed, and you plug in another sled or CPU compute module, and then you have more capacity there in the network to allocate across the vendors. So it's the flexibility and the agility of these cloud platforms is what will make this a success.
It's not a zero-sum game. So, Rob, do you see the same, or do you see additional aspects of the hardware provisioning?
Yeah, I see a lot of the same aspects that Declan has described, and as far as the actual deployment of these containerized services, the operator and the system integrator will basically bear the responsibility of ensuring what the utilization of their physical servers is going to be, but based on the performance characteristics that the vendors can give for each individual containerized microfunction. So yeah, I see a lot of the same benefits that Declan has mentioned, but again, the where I see what will be new is the shift of responsibilities from the vendor community to the operators and their system integrators.
So the shift in new responsibilities. So talking about that, do you see the operators needing to take more responsibility for the whole modeling and resource calculation process when in the past they depended on their vendors to do all of that?
Absolutely. In the legacy networks, the vendors brought the whole package, and usually on dedicated hardware, which minimized the amount of testing they would have to perform to get the performance characteristics. So it was a very known performance characteristics, but again, with that model, it's a forklift operation to replace it. So now with 5G, the vendors, they're not going to be able to model every type of hardware implementation and networking configurations that multiple vendors or multiple operators will have, and also the interaction with in a multi-vendor environment with other network functions. So it's definitely going to be more the responsibility of the operators and system integrators to gather that, model it, and then measure it after it's been deployed. So that's where I see a lot of the responsibility shifting from the vendors to the operators.
And we're only really just at the beginning of being able to build these traffic models. We have people asking some questions about, going forward, we'll ultimately be able to do machine learning, but it seems like we've still got a lot of data sets to collect before we can do that. So with that, we're just about out of time for Q&A. So I'd like to thank our speakers and send back to Nancy.
All right. Thank you so much, Sue. And thank you so much for attending this Fierce Markets webinar sponsored by HPE and Intel and for submitting so many great questions. I'd like to thank our speakers, Sue, Rob, and Declan for participating, and Hewlett-Packard Enterprise and Intel for presenting today's webinar. This webinar has been recorded, so you'll be able to access the recording within 24 hours using the same audience link that was sent to you earlier. So thank you again for joining, and let me circle back and remind you we have some great upcoming webinars. We have 2 more webinars in this series, the 5G Orchestration and Automation Towards Zero-Touch Service Management webinar coming up next week on October 10th, and the 5G Integration and Operations in a Multi-Vendor Container-Based Architecture webinar on November 7th. This concludes today's webinar. Thank you so much for joining us.